What if the materials we use every day could do more? What if they weren't just static objects, but could actually respond and change all on their own? We're about to dive into this incredible world of smart materials and check out the new models that are finally letting us unlock what they can really do.
Okay, here's a fun one for you. Sounds like the start of a riddle, right? You've got your phone's battery, this rigid little powerhouse for your digital life, and then you have a squishy, flexible robot that might one day be performing delicate surgery. I mean, what on earth could possibly connect these two things?
Well, the answer is actually pretty cool. Both of them depend on a special group of smart materials. It turns out, at their very core, the battery electrodes and the robot's muscles are made of stuff that physically swells up or shrinks or bends as chemical reactions are happening inside them.
So to really get this, we gotta look at a process you could almost picture as, well, materials breathing. Now, scientists have a fancier name for it, of course. Chemo-mechanical coupling.
Okay, and here's the absolute key. This is not a one-way street. It's a feedback loop, a two-way conversation. A chemical change, say lithium ions rushing into a battery electrode, makes the material expand, but then, and this is the really cool part, if you physically stress that material, squeeze it or stretch it, that actually changes how the chemical reaction itself happens. Let's break this down with something super simple. Just picture a dry kitchen sponge. When you add water to it, that's our chemical change, it swells up, right? It totally changes its shape. Now, if you squeeze that wet sponge, that's you applying physical stress. You force the water out, changing its chemical state again. That little back and forth is the whole idea behind chemomechanical coupling. So you can probably guess, for engineers and scientists, this whole breathing thing is both a superpower and a massive headache. Using it is the key to all sorts of new tech, but trying to predict it, that has been incredibly tough. And that brings us to what we're calling the modeling dilemma. So for the longest time, the only way to even try and simulate these changes was with these super complex 3D computer models. And they're powerful, for sure, but for the very things we're most excited about, like super thin battery electrodes or long, flexible robot arms, they are painfully slow. We're talking days, maybe even weeks, for a single simulation. So what everyone was desperate for was a shortcut, right? A model that was fast, efficient, but, and this is the important part, didn't throw accuracy out the window. So how do you fix a problem that's just too big and slow? Well, it turns out the answer was to think simpler, way simpler. Researchers came up with this really elegant and radically different solution, a brand new one-dimensional model. Instead of trying to calculate all the forces on every single tiny point in a big 3D object, these researchers had a brilliant idea. What if you could capture all of that complexity with just a single flexible line? They used this special mathematical tool called a Courseratte rod. Think of it like a super smart piece of string. It's a line that already knows how to bend, twist, and stretch, capturing all that important physics, but in a much, much simpler package. And this right here just shows you how clever this whole approach really is. You can see how the model mathematically maps that entire complex 3D transformation, all the stretching, the bending, the twisting, onto that one simple line. It's a way to get the essential physics without all the heavy computational baggage. But look, a simple model is great and all, but it's totally useless if it doesn't actually work. So the next step, the big one, was to put this beautiful new theory up against some cold, hard, real-world data. And this is it, right? This is the moment of truth for any new scientific idea. Does all that elegant math on paper actually predict what's going to happen in a real lab? And the answer? Well, you can see it right here, is a huge, resounding yes. Look at that. The red triangles, that's the data from a real experiment. And that solid green line? That's the prediction from their new 1D model. It's not just kind of close, it is a nearly perfect match. I mean, this is that aha moment. It proves the model isn't just fast, it's unbelievably accurate. So what's the secret sauce? Why is it so much better? Remember that feedback loop we talked about? This model is one of the very first of its kind to get that two-way coupling right. It actually understands that pulling on the material can make it absorb more moisture, something called stress-assisted diffusion. Older models that just ignored this, well, that's the dashed blue line way down at the bottom. They completely, totally missed the mark.
And believe me, this isn't just some abstract win for the academics. This predictive power has massive implications for how we're going to design the technology of the future.
So having a model this fast and this accurate, it's like we've been trying to design with a blindfold on, and someone just handed us a high-powered microscope. All of a sudden, we can rapidly test out new ideas to create battery electrodes that don't crack under stress. We can design way more nimble soft robots, create powerful little engines from hydrogels, and invent a whole new class of smart materials that can intelligently respond to what's around them.
And this whole idea isn't brand new. As this quote from some earlier research shows, the dream has always been to get the super precise control over how materials change shape. Like making a robotic finger curl just so, without it twisting sideways. Well, with this new model, that kind of precise control is finally moving out of the realm of dreams and into practical, real-world engineering.
When you boil it all down, it comes to this one simple but really powerful idea. The physical stress from all those chemical changes, that's a huge reason why things like our phone batteries eventually fail. They literally swell and shrink until they crack. So if we can accurately predict exactly where and when that stress will cause a problem, we can design things from the start to last longer and perform way, way better.
What this breakthrough really does is hand designers a brand new, powerful toolkit. It takes a lot of the guesswork out of engineering these really complex materials. And that just leaves us with one really exciting question to think about. Now that we can actually predict, and maybe even teach, materials how to move, what incredible things are we going to build next?